Our next speaker is Mesut Durukal, who is a QA and test automation manager at Siemens. He has 7 years of experience in defense industry, serving as a manager of verification and validation activities. And today he will tell us about how the artificial intelligence will assist us in the future of software testing. So let me add Mesut to the stream. Hello, it's great to have you here today.
Hello. Hi, Alexandra. Thank you.
And I will add your presentation.
Okay.
You can start now.
Okay, thanks so much. And let me start my presentation. Okay, so hello everyone, welcome to my presentation. I'm very happy to be here because I see there are great talks and I hope you are enjoying it. And in this session, as Alessandro told, we are going to talk about some practical applications of machine learning in software testing. So as you already know, my name is Mesut and I'm sharing some contact information for me. So please do not hesitate to reach out to me. You can ask your questions on any of the platforms, and I'll be answering the questions coming from the chat section. And even after the talk, I will stay for a while still to answer your questions. So this is the brief agenda for the talk. As I told, we will discuss some practical applications of machine learning in software testing stages. And first of all, I will start with a quick background of the working principles. And I will make a quick reminder for the working principles of machine learning algorithms. And especially from the software testing perspective, we will take into account the working principles and the learning mechanisms. And then we will start discussing what we can do with machine learning assistance in software testing stages. And we will try to do that in a systematic manner. I mean, we will investigate what we can do in different stages, starting from defining test cases, then how can we continue with implementation of test cases, and finally what we can do for the maintenance of test cases or the bugs, defects, or vulnerabilities that we found on the product. As you know, at the end of the software testing lifecycle, if we find some vulnerabilities on the product, we report them. But there is a great data on the bugs, on the defects. We have lots of fields on the issues that we create. We have the creator field, we have the assignee field, we have the description of the bugs, and lots of different fields. And at the end of my presentation, I will share a case study in which I try to classify the bugs according to their severity levels. I mean, in our real-life project, we have a track management system, which is maybe all of you know, Jira. And when you export the bugs, you can have the list of the bugs that you create and you assign to the developers, the development team or the product owners. And in each bug, we have a severity level. If it's a critical bug, then we have a high severity level. Or if it is not that critical bug, then we have lower severity levels. So in my study, I'm trying to classify the bugs, the upcoming bugs, to their severity levels due to their descriptions. After we model our system according to the past experiences, the past samples, because we have lots of samples, and in each of them we have already the descriptions and we have already the assigned severity levels. So for the upcoming levels, we will see how it works. So let's start with the introduction part. And in this section, we will quickly remember how it works and how the machine is learning our system and how it is modeling or how it is constructing a model to predict the upcoming samples. So first of all, firstly, let me start with how or why we are doing this, right? Or why we are searching for adaptations of machine learning into software testing. What is the relevance? Normally, okay, some data scientists are working on machine learning algorithms, some researchers are working them, but for software testers, what is the relevance? Or do we have to do this? Do we have to search for adaptations of machine learning? I think yes, because we have some challenges. Nowadays in the software market, there's a great rivalry. So everyone is trying to be the first in the market. So everyone is in a rush. We have a limited time to deploy our services, deploy our product, and in this limited time to verify the context, we have a complex structure, or we have a complicated context, because the products are integrating to different platforms. There are lots of integrations, there are latest technologies inside the products, and we have a limited testing window. So there are great challenges from the software testing perspective. For example, I remember in one of my deployment activities, I had only 1 hour testing window to complete all the end-to-end test cases. And all the developers were waiting in front of me. They were asking me if everything is okay, if they can deploy, if they can go to live. So you are under stress. I think all software testers experience this stress, especially in the deployment windows, or just before going to live, just before going to production environments. So due to these challenges, sometimes we have a limited capacity, and we are having some difficulty to handle all these challenges. We have some limited resources, we have some limited headcounts, and limited time especially, and lots of things to finish. So we are searching for adaptations, or we are searching for some help from some different platforms. And at this moment, machines and machine learning is a great candidate to help us, to human beings, because okay, we know that machines are created by human beings. They have already some limited capacity, but of course they have some definite advantages as well. For example, machines do not forget, right? For example, human beings, it is a very likely possibility, but for a machine, it doesn't forget. If you put an information into a machine, then unless you delete it, it is always there. And the machines do not get tired. For example, at the end of a working day, for a human being, it is very likely to get tired and overlook some vulnerabilities. For example, at the end of the day, a tester can miss some bugs because he will quickly do what he should do, because it is already late, and he is or she is trying to or wanting to go to home. So the concentration or the motivation is decreasing at the end of the time, at the end of the day, and she will get tired. But for the machines, it is not the case. So it is performing almost at the same level for the whole duration. And finally, for the resources manner, it is very easier to add some additional resources. I mean, when the resources is not sufficient in a project, it is not very easy to add some additional people or additional colleagues in the team, because it requires some adaptation time for the new comers to the team. But for a machine, if your resources are not sufficient, if you need some extra resource, then just create a virtual machine and add it. It is that easy. Especially, it is easier than adding a new human being into the team. And we already started to see that machines started to overperform human beings in different platforms. For example, in some games, we see that they are beating human beings. For example, in the Go game, which is one of the hardest games in the world, machines or robots started to beat the champions of the game. And in some different other areas in our daily life, we see that machines or machine learning algorithms are helping us, right? For example, when I'm checking my emails, or when I'm responding some of them, I see that even after I start typing my response, then I see that some of the sentences are automatically completed. For example, I start with hi to the responder, and I see that the name is automatically completed, because it knows that it's coming from whom. And it knows that the way I respond, I mean, if I start with hi, then it's from the past experiences, it learned that I will complete the rest with the name of the sender, right? So it learns how it works, and after it learns how it works, after it constructs the model of the system, then for the feature, for the next coming steps, it makes or it performs some predictions. It predicts the next steps or next action items. For the software testing applications, we will see the same. first machines will learn how our system will work, and then he will perform the predictions, the further action items. We will see them one by one. And at this moment, let's quickly remind how it works. First of all, it will let me illustrate this with our real life. For example, if you come to me to test your system, if you ask me to test your system as a tester, then my response would be, okay, I can test your system. But first of all, teach me how it works. First of all, give me some information. First of all, give me some data about your system. I mean, if I send a request to system, what should I expect, right? As a tester, I should know the expected results, because otherwise I cannot assert the results if it is the correct one or the wrong one. I should know in advance, I should learn in advance how your system works. So it is the same for the machines. It should learn how it works, and then it can predict the further action items or the further predictions. It can work for the API side or UI side of the system. I mean, if your product is including the APIs or the user interfaces for the end users, then we can apply the algorithms for both of them. I mean, we can apply from two different perspectives. For example, if we have some APIs, the machine can learn that how the system reacts to some unauthenticated requests. For example, an API works with a response system, right? If it's a REST API, then normally what we expect is to send a query to the system and get the response with the response code. And if it is not an authenticated one, then most probably we will have a 401, right? Which is an authenticated response, or 403, whatever. And if we send a request which is in a bad format, then what we expect is 400 response code. With providing all this information to the system, then it learns how it works. And for the next request, which is in a bad format, then its expected response would be a 400 response. And similarly for the UI side, it can learn how it works. I mean, it can navigate between different pages of the system, and it can check how the buttons are working. For example, it's very similar to what we do when we are performing exploratory testing, right? I mean, when the first time I'm testing a system, the first thing I do is to navigate between pages of the system, pages of the site, and click on some buttons to see how it works. When I see or I feel an area, a field, a text field on the page, then when I submit the button, then a request is going onto to the server, and I'm navigated to another page. Or maybe a balloon appears on the page as a response. I don't know, but when I try this, I learn and I see what is the response or what is the reaction of the system. And in the next run, I already know, or I will be already knowing what my expected response would be. So after this quick background, let's see what we can do with the assistance of machine learning in the software testing stages, different stages. So, and as I told in the beginning, I will try to investigate this in a systematic manner, one by one, in order, starting from the definition stage and going with implementation stages, and finally the maintenance stage, because this is an ordinary software testing lifecycle. As a software tester, we start our activities in a project with defining test cases across features or across requirements. Then we implement, if we are performing test automation, to inject them in our pipelines, to implement them, to adapt them in our pipelines, to be able to automatically run them with jobs on our pipelines. And finally, after we implement them, we execute them, even triggering manually or automatically on our pipelines. And finally, we maintain our test cases. I mean, if a requirement is updated, then we update our test cases as well. Or if we find some bugs or defects on the product, then we create the issues to the owners of the feature, and we maintain and we update the status of these issues. I mean, when the bug is created, just after created, we set it into open status, and when someone started working on them, we set it to in work status or something else, or in progress status. And after we test, and if we approve the fix, I mean, if we think that the fix works, then we set it into accepted status, right? We update it and we continue our activities with the maintenance activities. But the key point here is, in each two consecutive activities, there are some input-output relationship. I mean, when we create our test cases, we build a traceability between our test cases to the features, because we build our test cases across features or functions or requirements. So there's an input and output relationship. There's a mapping between these two. Or whenever we create a bug, we are setting an annotation or setting another field to state across which feature we create those bugs. So we will utilize this input-output relationship to perform our activities, because when we learn that some type of test cases are created across different features, for example, when we see we have an upload feature, for example, in our IoT platform, we have a data upload feature, right? And we can learn that across upload features, we can create some data sending test cases with some different data types. For example, we can try sending string values, we can try sending integer values, negative values, lots of different test scenarios. But the key point here is across uploads feature, we can define some negative and positive test scenarios. So we will get advantage of this relationship, the input and output mapping, and in all stages we will see what kind of activities we can do with the help of machine learning, because they are all reducing the manual effort, right? Because at the beginning we discussed that we have some limited capacity and we have some challenges to complete our test cases in a limited time. So if we succeed somehow to perform these activities automatically with the help of machine learning, then the manual effort and time needed to complete these activities will be reduced in a great extent. So let's start with the first cycle, which is the test case definition. As I told, when we start to our testing activities, the first thing we do is to analyze the requirements and to generate some test cases to verify those requirements. So as we discussed, first of all, if we are wanting to create some test cases, we should know the product very well, right? Because in a project, software testers are one of the members who know the product best, because you should know all the possible scenarios or all the alternative paths which can customers try. And after you know each possible scenario, then you can create your test cases. So let's go over one sample scenario. It will be more clear when we go over some examples. For example, in the slide, we can see an API, which is the API of a library. And in the library, we have some books. And for all the books, we have some information related to the relevant book. For example, when we query a specific book, then we can learn the publish year of the book and the price of the book, what is the cost of buying that book, and the ISBN number of the book. We can get those information. We can pull those information from the server. And what we can see right now after checking this structure is, now I can see that, okay, there are some entities in the API, the response structure, and in each entity, I'm able to get the information to the relevant book. And I have three fields, which is ISBN number, the price, and the year. And I can see what type of data exists in those fields. For example, I see that the price is expressed with some double value, or the published year of the book is expressed with an integer value, or ISBN is expressed with a string value with some dashes to distinguish the fields of the ISBN number. So I can see how the data is formed, how the structure of the data is looking like. And what I can do next is I can generate some test cases to perform my positive and negative scenarios. For example, if I inject a value which is not a string value into ISBN number, then my request would be a wrong format request. So already I generated that test case, which is a negative scenario. And similarly, I can generate some positive scenarios as well by injecting different data values in the expected format. So, for the UI side, it works a little slightly different. This time, the images or the icons on the page are very important, because when I go to an online shopping site, I can use the site, right? I mean, nowadays, most of us are ordering or buying something from the online shopping sites. And when I go to a new shopping site for the first time, I can use the system. No one has to teach the system or the site to me, because I already know how it works. But how do I know already? Because I used some different systems in advance. For example, okay, maybe not that site, but some other sites, I already used them. And I already know how or what a basket means or a basket icon means. I already know that if I see it, I can understand that it is the shopping cart of the site. And when I order some items, it will go or they will appear in the basket icon. So I can learn something from my past experiences, and after I learn them, I can use the newly created system or the newly created site. So due to my past experiences or learnings, I can predict what I should do. For the system that I'm testing for the first time, whenever I see a shopping cart icon, then I can imagine that I can test ordering something scenario. And whenever I add some items to the cart, then if I go into the shopping cart, then I should expect all the items to appear them, right? Because I already ordered them. So what I'm trying to tell is we can predict the action items across our steps on the site due to our from our past experiences or past learnings. So it works similarly for the machines. When we provide lots of different icons with the meanings from different sites to the machine, then a machine can already learn that a basket stands for a online shopping cart. And similarly, all the icons they can the machine can learn the meaning or the functionality of all the icons or images on the page. And after it learns that, it can generate all the relevant test cases in the positive and negative scenarios. And after we define our test cases, the second thing we do is, as we saw it in the first slide, the implementation tasks. Then we have to automate our test cases with developing the test code to be able to adapt them in our pipelines. And for this purpose, we have to develop our test code. And it is sometimes a very cumbersome issue, because after we develop our code, most probably we are sending it to a colleague in the team to review, right? Because we all have some code quality issues, and we have some code review tasks. So sometimes it is longing very, or we can simply say that it is a time-consuming issue, because I'm sending my code to a colleague, and then he reviews. And if he finds some vulnerabilities in the code, then he sends it back to me to fix my code. Then I apply my fixes, and then I send it back to him, and we lose some time. So to reduce this waste of time, we can make use of some machine learning algorithms. For example, for the example on this slide, we have a pair of input and output. For the provided input, normally we expect an output vector. And for a human being, it can be, or it may be not very trivial to find the relationship between the input and output. But for a machine, it can be very quickly understand what is the relationship between input and output. I mean, for this pair, all the values in the input are multiplied with 4, and all the positive values are filtered out. And finally, they are sorted starting from lowest to the greatest. So all these needed steps are found by the machine. They can be found very simply and quickly. Then after it's found what is needed to reach to the expected output, then the relevant operation is very simple to adapt. I mean, after it understands that the input values are or should be multiplied with 4, then the multiplication with 4 code is standing already there, and it can apply the relevant code to perform or to reach to the expected output. So in this way, we will perform our activities very quickly when we compare to the manual efforts that we perform as human beings. And for the UI side, I think all or most of the software testers are aware of this issue. Front-end automation can be sometimes a nightmare for software testers because it is not stable for most of the time. After we find the elements with their locators, with the traditional locators such as IDs of the elements or the XPaths or some CSS paths of the elements, then they may be updated by the developers. And if they update the ID of the element, then your test code is broken, right? So it is not stable. So sometimes it is very challenging. And how we can solve this, instead of applying traditional XPath selectors, we can find or we can locate the elements according to their visual representation. I mean, why are we trying to locate the element by its ID? Because we are already knowing that or already knowing which item we are looking for. For example, if we are looking for the online shopping cart, then why to use the ID? Or just we can visually search for the cart right on the page, and we already teach our machine how a cart is standing for or standing like, how it is looking like. And after it learns, it can quickly find by its visual representation. And after we implement and develop our test code, the next thing we should do is to execute them. And during the execution, we can still collect some data, right? For example, we can collect the execution durations in each run. I mean, in the first run, I can check the execution duration, and if it is 10 seconds, for example, and in the second run, maybe it's 15 seconds, in the third run, it is again 10 seconds, then my machine can learn that, okay, for this test case, the expected execution duration is around 10 seconds. And after the machine learns this, if an unordinary or unexpected situation occurs, for example, if the duration lasts for, let's say, not 10 seconds, but 30 seconds, then the machine can warn me, right? Okay, please check this because it is not the expected result. There is something wrong in this execution. So in this way, I can automatically detect if a configuration is done wrongly or if there's something else configured in the wrong way. And finally, after we develop our test cases, we develop our test code and execute them. Finally, we have some maintenance issues. For example, the refactoring of the code. And we can do that with the help of machines. For example, we can have some anti-patterns or best practices in the code. If we teach all this to our machines, for example, if we teach our machine that embedding some magic numbers into code is not an expected situation or not a best practice. It's an anti-pattern, right? To having some magic numbers in the code. So if we teach this to the machines, then they can warn us automatically if they detect some embedded numbers or magic numbers inside the code. So we can perform our refactorings by the help of artificial intelligence assistants. And finally, we can prioritize our test cases, right? Because infinite testing is not possible. So in a limited time, we have to select some of them. We have to select the test suite, select a subset to be executed, because we don't have time to execute all of them. So how can we select this subset? Or how can we prioritize these test cases? We can, again, from the past samples, in the previous runs, we already know which test cases found most errors, right? Or most defects. So we already know which cases are most likely to find some defects. So we can, from the past experiences, we can predict what is the best subset to be executed in our current run. So I'm closing to the end of time, so I will go quickly to my case study and at the end of my presentation, and it is related to bug management. And for the bug management, we can automatically assign those severity levels. And let's start investigating it over the real-life scenario. It will be more clear to understand. In this project, we have 6 different severity levels. In each bug that I create as a software tester, I set the severity of the bug to one of those 6 severity levels. And from those 6 severity levels, 2 of them are regarded as not real bugs, but as change requests. I mean, severity level 5 and 6 are regarded as not bugs, but change requests. So apart from them, I have only 4 levels, and severity level 1 is the ones which is related to human life issues, safety issues. So in our current project, we don't have any severity 1 level bug. So actually we have 3 different severity levels for our bugs: 2, 3, and 4. And of course, we are dealing with some string values. I mean, as you can predict in some different studies, we can be dealing with images or sounds or videos or something else. But for the bugs, we are typing the description of the bug. So they are string values. So what I'm trying to say is we are dealing with some natural language processing tasks to extract the features of the bugs, the description of the bugs. And now I will share the results of this study. After we extract the features of the bugs, then we model our system, and machines are trying to predict what are the labels of the bugs which we do not provide. And in this distribution, we have such a kind of number distribution for different classes, for class 2, 3, and 4. And we see that for most of the bugs, we have class 2 severity level. And for this distribution, this is the confusion matrix of the results. And we see that it is in an acceptable range. It is a 73% success rate. But I thought that it can be improved. And I started to think about what can be the improvement points. And we saw that in the previous distribution, it was not a very balanced distribution, because most of the bugs were in class 2. And what I did next is to combine class 3 and 4 together across class 2. It really makes sense, because in our project, class 2 bugs are regarded as release blocker bugs. So deciding if a bug is class 2 or not makes really sense in this project. And after this distribution, what we have is 82% success rate. And we see that over the confusion matrix, it is much more balanced, and we do not have any bias. So this is the benchmarking results coming from different algorithms. I tried lots of algorithms, and if you are really interested in the details of these implementations, please ask me from the chat section, because I'm running out of time. I do not have time to go deep in the algorithms, but if you are interested in the details of the implementations, please do not hesitate to ask your questions. And finally, we can discuss that there is no absolute truth in this study. I mean, okay, as human being, I'm creating a bug. I'm setting the severity level of the bug, right? But who can say that my decision is the correct one? because I mean I create a bug and I'm setting it to severity 2, but someone else can regard this as not severity 2 but severity 3. So perhaps machines are working more consistently than the human beings, because as a human, I'm not checking all the other samples in the project. I'm only creating my own bug, and I'm making my own assumption, my own evaluation. So who can say that I'm creating my bug very consistently with all the guys in the team? So that is what machines are doing to check all the samples in the data pool, and most probably it's working more consistently than the human beings. And of course, there are some further things that we can do to improve the algorithms. And apart from classification, what we can do is clustering of the bugs. And by constructing some clusters, some groups, we can see if some bugs are heaping together on some certain features. For example, after monitoring or making clusters, we can see if a bug group is heaping together on a specific feature, then I can check if something is wrong on the feature itself. And it is the visualization of the clusters. We can see that some bugs are heaping together. We can divide them in some or distinguish them with some slices on the 3D representation. And that was another alternative that we can do, the classification or the clustering. So this is the last summary of what we discussed in the session. There are lots of things that we can do with the help of machine learning, starting from the definition of test cases, going with implementation of test cases, and finally maintaining our test cases and the bugs that we create. There are lots of things that we can do with the assistance of machine learning and artificial intelligence. So as a software tester, sometimes we can think about the relationship between the machine learning algorithms and our activities. There are really lots of things that we can adapt from machine learning algorithms in each of the stages that we apply in our life cycles. So finally, this is the main idea of this talk. This was the main idea. We can get advantage of machines from different perspectives, because we know that they have some limited capacities in certain ways. But of course, there are some advantages that we can utilize from machines and improve our processes and the stages of our life cycles. So thanks so much. Thanks for listening to me. And now, if we have some time, I will check if we have any question, and I'll try to answer them. Thanks so much.
Thank you, Mesut. Thank you very much.